Today we're going to look at how we can make our programs simpler and faster through bitwise operations. Bitwise operations are very common among hardware designers and assembly coders because of their simplicity and speed. Our objective today is to implement a scheduling comparison routine that compares two set of schedules and let us know whether the days of a week that we requested is fully matched or fully offered by all the days that are available in a week. Looking at example here, we can see that Sunday, Tuesday, Thursday, and Saturday are available days, and we need Thursday and Tuesday, and in this case, it's a match. However, if we request Wednesday, it doesn't really matter whether Saturday or Sunday are offered. The fact that Wednesday is not available disqualifies this comparison. This routine is very simple, very easy to implement using the conventional approach. We simply loop through every day in a week and compare whether a day we want is not offered. When we run this loop, we check the first day, which happens to be Sunday, and then we check Monday, and Tuesday is a wanted day and also is offered. The moment we reach Wednesday, we realize this is the day we want, but this is also a day that's not available. And therefore, we conclude that the event in question does not have all the wanted days. Next, we're going to simplify this routine using bitwise operations. The first step is to look at the schedules as digits. So we have to think in binary. For every day that's offered or wanted, we're going to mark the day as 1. For days that are not offered or available or wanted, we're going to mark it as 0. Using a binary calculator, we can easily see that the decimal presentation of the available days is 85. One common misconception about binary computing is that computers compute and stores information in ones and zeros. Well, although information is stored and represented in ones and zeros, computers actually store information in chunks of 8 bits, and each chunk of 8 bits is considered a byte. In the conventional approach, we're using 7 variables, that is at least 7 bytes, to store a schedule. But when we pack the digit, each byte has 8 bits, and we have used only 7 out of 8 bits. Right? There were 8 bits in a byte, and there are only 7 days in a week. So we can take full advantage of this. Next, let's see what we can do at the atomic level of our data. The first operator is the AND operator. It requires both operand to be 1. So if either one of them is missing, your result won't be 1. The OR operator, expressed as a pipe sign, on the other hand, requires only one of the operand to be true. So if you have 0 or 0, your final result will still be 0. The rest result will all be 1. An interesting operation is the exclusive OR. The easy way to remember the result of an exclusive OR is that the result is always 1 if the two operands are different. If two numbers are the same, their exclusive OR computation will result in 0. As a matter of fact, in assembly code, it's common to use the exclusive OR of two of the same variables to zero out the value of a variable. Now let's look at how we use these operations. The first thing we want to do is to demonstrate how to modify a value. So in this case, we're going to modify the flag or the digit at the third position. So we're going to use the OR operator. We can also use the exclusive OR operation to flip the digit at the sixth position, and in this example that would be Sunday. So the first time we run it, we'll have one exclusive OR with 1, and 1 and 1 are the same, so you get 0 instead, and that would uncheck Sunday. And if you run the same operation again, you will be computing the exclusive OR between 0 and 1, and that will give you 1, which will check Sunday again. In other words, exclusive OR operator is very convenient to implement a ping-pong switch. In addition to modifying specific bit of a digit, we can also check whether a certain digit is checked or not. In this case, we're going to use the AND operator to check whether we have the second position available, which is Thursday. As mentioned earlier, when we feed numbers to a computer, we are dealing at least 8 bits at a time. This means when you compute between two numbers, you are dealing with every bit in those two numbers at the same time. Next, we're going to devise a formula that tells us whether there's a day in a week that is wanted but not available. So the first step of the calculation is to find out all the days that are either available or wanted, and we perform an OR operation between the two numbers. The next step is to subtract the days that are already offered. We ended up with a number in the fourth position that is not 0. The fact that the final result is not 0 indicates the existence of a day that is not covered. Now let's test this formula on the two examples we illustrated before. The computation cannot be simpler. In the eyes of computer, it's asking itself whether 85 is the same as 85 or 93 is greater than 85. Because the computation is so simple, it happens extremely fast. In the conventional approach, we have to negate the value, compare it, and do this at most 7 times, and that gives us 14 operations. With our new formula, we're performing a much faster set of operations. The bitwise operations are implemented in the hardware level, so they're extremely fast, and we're doing a OR computation, a subtraction, and a comparison. So that's 3 really fast operations. In addition to their speed, bitwise operations have also brought us unprecedented portability. There's a fundamental difference between programming logic and a simple expression. In the first case, we'll have to write some sort of loop. Imagine there are hundreds or thousands of events to check. We have to perform that 14 operations on all those 1,000 events. But with an expression, we can easily attach that into a where clause in a SQL statement and filter out all the qualifying events in a split of a second. The problem we solved today is very simple to begin with, but we made it simpler and a lot faster with bitwise operations. Sometimes we just have to look at things differently for a much better solution.